All right, 53. Starting with the orbital diagram of a boron atom, describe the steps needed to construct hybrid orbitals appropriate to describe the bonding in BF3. What is the name given to the hybrid orbitals constructed in A? Sketch the large lobes of the hybrid orbitals constructed in part A. Are there any valence atomic orbitals of B left unhybridized? If so, how are they orientated relative to the hybrid orbitals? Well, let's start with A. Right, so this is our electron configuration for boron. Right, we have 3 valence electrons. 2 of them located in the 2s, 1 of them are located in the 2p. So if we're going to hybridize for 3 bonding positions, right, boron's got to bond to these 3 fluorines, we promote an electron from the 2s up to the 2p. And now we mix the 2s shape, right, that sphere shape, with 2 of the 2p's. And I get 3 bonding positions, right, which are hybrids, right? They're 1 part S, 2 parts P, right? This is what it means to be an an sp2 hybrid. So these are half-filled hybrids, right? So they're good for overlapping with the half-filled p orbitals of fluorine to get bonds. And this is what they look like, right? So they're kind of a big lobe and a little lobe, right? Orientated 120 to each other, right? Boron nucleus is in the center. So that unhybridized p is sticking up out of the plane, right? It would be perpendicular to the plane here. So these hybrids are 120 to each other. The unhybridized p is sticking up outside the plane. So this is what this thing looks like. All right. The hybridized ones are for bonding, and the p shape is left there, right, without an electron. All right, with boron trifluoride, right, you have sp2 hybridization, right? We have these half-filled sp2 hybrids ready to overlap. Fluorine, as we know, has a half-filled p. So when that half-filled p of fluorine overlaps with this half-filled sp2 hybrid, I get an sp2 p overlap sigma bond. That's what a sigma bond is. It's an overlap between the nuclei, right? Imagine the big B is the nucleus of the boron, and the big F is the nucleus of the fluorine. So these electrons are between the boron and the fluorine. That's what it means to sigma bond. So I've got 3 places to do these sigma overlaps with the boron. So we've got a p sp2 sigma bond. I mean, this is the whole point of hybridization, right? Is to rationalize, how I get this planar trigonal overlap, molecule where I'm overlapping with the boron and the fluorines. So that's what the line represents, right? It represents a p sp2 sigma bond, right? The electrons are shared between the 2 nuclei. Now I added to this, right? I was looking at sulfur dioxide, right? So we have a double bond with sulfur dioxide. So again, right, if you look at the electron domains here, right, you've got a planar trigonal geometry of all the electron domains around sulfur, right? So this is an example of sp2 hybridization. Now that one pair is sitting up there in one of the sp2 hybrids, and the other 2 sp2 hybrids are half-filled, and I've got an unhybridized p with sulfur. All right, so that's sticking up out of the plane. So that's overlapping with an sp2 hybridized oxygen, right? Again, it's a planar trigonal geometry of all the electron pairs with this oxygen. And again, p is sitting up out of the plane. The other oxygen, you've got 4 electron pairs, right? A tetrahedral arrangement of all the electron domains around the oxygen. So this is an example of sp3 hybridization. So I've got an sp2 hybridized oxygen overlapping with an sp2 hybridized sulfur. That's going to be a sigma sp2 overlap. Now, the double bond. That's going to involve these unhybridized p's, right? There's electrons up in these unhybridized p's of sulfur and oxygen. And what they do, right, a p is a dumbbell shape, is they overlap and they touch above and below the internuclear zone, right? So there's basically outside this sigma overlap, touching above and below. So that's what a pi bond is. It's a 2 unhybridized p orbitals touching above and below a sigma bond. So when I look at a double bond, it's 1 part pi bond, right? This unhybridized p overlap, and 1 part sigma overlap. In this case, it's an sp2 sigma overlap. So that's that's what a double bond is: 1 part pi bond, 1 part sigma bond. All right. So with 55, indicate the hybridization of the central atom in boron trichloride, and this anion, and carbon disulfide, and germanium ditetrahydride. So draw the Lewis dot structure, predict the geometry. If I have a 120-degree bond angle, like I do with planar trigonal, it is sp2 hybridization. That's how easy it is. You just predict the geometry, and from that you can predict what hybridization scheme you'd need to have that geometry. So when you do the Lewis dot structure for AlCl4 minus, we have 4 bonded pairs around the central atom, tetrahedral geometry, 109.5 degree bond angle. That's sp3 hybridization. All right, so this is where we get 4 bonding positions around the aluminum. Carbon disulfide had to loan pairs of electrons from the sulfurs to form double bonds with the carbon. So a double bond is 1 part sigma bond, 1 part pi bond. And in order to get a pi bond, you need an unhybridized p orbital. So when you have 180-degree bond angle in these 2 double bonds, the only option is sp hybridization. So we just go off the geometry. If it's a linear geometry, it's sp hybridization. 4 bonded pairs around the central atom, no lone pairs, tetrahedral geometry, sp3 hybridization. All right, now A, B, C, D, I added an E. All right, so for this one, we have sulfur tetrafluoride, right? When we count the electrons, do the Lewis dot structure, predict the geometry, we're breaking the octet rule around the sulfur, right? So I need 5 bonding positions to put these electrons around. 3 half-filled ones to overlap with the fluorines, and I need an unhybridized orbital for that lone pair. So in order to do this, right, if I'm looking at the electron configuration for the, let's go back just one, looking for the electron configuration around the sulfur atom, we've got a neon core, right? We've got 6 valence electrons for the sulfur. In order to get 5 bonding positions, I'd have to, use all 3 of the P's, right? So blend the 3 P's with the S, and I now have 4 hybrids. Well, I need a 5th one. So in order to do that, I've got to borrow 1 from the 3D. So when you need 5 bonding positions around the central atom, right, you're going to break the octet rule. You need to start hybridizing d orbitals to justify this. So there's sp3d hybridization. That's going to be when I have a trigonal bipyramidal geometry of all the electron domains, and then there would be sp3d2 if I needed 12 electrons around the central atom, 6 bonding positions. So that lone pair right there, right, are those electrons, right? So we have a filled sp3d hybrid and 4 half-filled ones for overlapping with the fluorines. So sp3d hybridization gives me 5 hybrids. All right, so we're looking at a Lewis dot structure for glycerin. It's got multiple centers. What are the appropriate bond angles about each of the carbon atoms? What is the hybridization of these orbitals? All right, so I redid this drawing in a 3-dimensional way. So looking at carbon number 1 on the top, I've got 4 bonded pair, no lone pair, so that's a tetrahedral geometry, therefore it's sp3 hybridization. Looking at carbon 2, I've got the double bond, so right off the bat, I've got to have an unhybridized P, right? 120, why don't you just go off of the geometry? It's 120-degree bond angle. 120-degree bond angle is sp2 hybridization. Again, I need that unhybridized P for that pi bond and that double bond up there with the oxygen. All right, so those are the carbons. What are the hybridization orbitals on the 2 oxygens and the nitrogen atom? What are the approximate bond angles? All right, so looking at the nitrogen, I've got that lone pair pushing the bonded pairs away. So I'm going to get a 107-degree bond angle between the atoms. Trigonal pyramidal geometry, that's sp3 hybridization. All right, so a tetrahedral arrangement of all the electron pairs around the central atom, right, including all the electron domains. Lone pairs push harder than bonded pairs. All right, so looking at the oxygen number 1 on the top there, I've got a double bond, right? So it's sp or sp. Well, it's only got to be sp2 hybridization. Oxygen can only bond to two things. So if you get a sigma bond and a pi bond, that's it for oxygen. It's sp2 hybridization. Notice you can look at the geometry of the electron pairs, right? It's a 120-degree bond angle of the electron domains. All right, so sp2 hybridization. Looking at the second oxygen, I've got two bonded pair, two lone pair. Those lone pair pushing the bonded pair into a 105-degree bond angle, a bent geometry. Again, sp3 hybridization, a tetrahedral arrangement of all the electron pairs. We're supposed to count up what the total number of sigma bonds in the molecule are and what is the total number of pi bonds, right? So I got rid of any bondy looking things with the lone pairs, right? So I've got 1, 2, 3, 4, 5, 6, 7, 8 sigma bonds and 1 pi bond in the double bonded oxygen. All right, what hybridization do you expect for the atom indicated in red in each of the following species? All right, so we've got acetate ion. The carbon in red has a 120-degree bond angle, right? You've got a double bond, which means a pi bond, so an unhybridized p, so this is sp2 hybridization. If we're looking at the cation ion with phosphorus as the central atom, that's 4 bonded pair, no lone pair. That's tetrahedral geometry, sp3 hybridization. If we're looking at aluminum trifluoride, right? 3 bonded pair, no lone pair. We're breaking the octet rule here. 120-degree bond angle, planar trigonal geometry, sp2 hybridization. And if we're looking at the third carbon in this cation, we've got 2 bonded pair and a lone pair. All right, so a tetrahedral arrangement of all the electron pairs, trigonal pyramidal geometry. That's an example of sp3 hybridization.